Hello everyone, my name is Javier. I'm a software engineer here at the Hopsworks, and today I will be talking about how we migrate Hopsworks platform, the whole Hopsworks platform, to Kubernetes. And this migration started from version 4. Before we go into the details, I would like to show two tools that we will be using today. The first one is Visual Studio Code, for which I will be using only the terminal because I like it, and a tool called Lens. And Lens is a tool to monitor Kubernetes clusters. Before explaining how we did this migration, I will run two commands in this terminal. And I will explain the two commands later after, but I just want to start the deployment of the cluster, Hopsworks cluster, just right now before we go into the details. Sorry about that. Yes. Then these two tools. 1 year ago or so, we started this migration from the whole platform to Kubernetes. But first, what is Kubernetes? Right? So Kubernetes is a container orchestration tool. And then you may say, yeah, well, what is a container? Well, a container is an encapsulation of a program or an executable or just files or just data, just that. So in Hopsworks, each one of the services is right now a container, right? So if we go, I will use this paper to draw some terminologies and concepts that may be useful. So from version 4.0, we started the migration to Kubernetes. This migration, we did it from making all services containers. And a container is just a program that runs encapsulated inside this small box called container. For example, Python, let's say http.server. Right. And Kubernetes is in charge of interconnecting or making these many containers to interact one with each other. And you may say, yeah, but you don't need Kubernetes to do this intercommunication between containers, right? So you have Docker Compose, you have the Docker. If you think on one single machine, you can deploy all of these containers and they can interact with each other. And even if you have multiple machines, you may have the Docker Swarm or Rancher, for example. But Kubernetes is leading this way. Why? Because we are talking about Hopsworks, and Hopsworks, when running, it may have like near 100 containers. And simply Docker Swarm or Rancher cannot handle this as easy as Kubernetes does. So we started this migration by putting every service inside a container. And that includes, in concrete, RunDB, the Hopsworks application, Airflow, the HDFS, Hops, and many other services that you may know Hopsworks supports. When we started this migration, we thought on several milestones that we wanted to reach. One was the stability, portability, and of course, we wanted to abstract away bare metal issues or networking issues from our engineers, right? So we wanted also that engineers focus more on the product than actually on the platform that was running all the services. That's why we also selected the Kubernetes to be our infrastructure platform, because in the end, it's just an abstraction layer on top of nodes. So we don't care, or you as a developer, you just need to be aware that Kubernetes is up and running, and that's it. That's the only thing that you will need. Also, testability and portability, right? So imagine you as an engineer, you make a change in one of these services, you deploy, you test, something is not okay, then you go back, right? When you scale up this all over the services, this is quite tangled, especially when you consider that the time between this and this is can have actually more than 1 hour. That makes life for developers quite complicated. And also for the infrastructure team. Why? Because you need to provide a way in terms of resources for this loop to happen, right? And the previous setup with virtual machines was already quite complicated in terms of deploying it. And actually, to be concrete, before version 4.0, you needed 2 hours to deploy the Hopsworks cluster. Again, making this loop of changing and deploying and testing quite longer than expected. And but this is just the regular DevOps loops, right? So we needed to go from scratch, from containers, from code that goes inside the container, that goes to a deployment, that goes tested, and then go back, right? But what is the main deal with this? So there are two main terminologies in computer science, and one is imperative programming, and the other one is declarative programming, right? In imperative programming is the one that we started to learn in the schools. Like if you want that a program prints hello world, you simply said that the instruction print hello world, right? In the declarative way, some sort of speaking, you can say, I want a program that print hello world. Let's say main message hello world. And the underlying engine will make this happen, or will create a program that when you run it, will print hello world, instead of you setting up the program instructions. I won't go into the details about these two paradigms, but the main disadvantage of this is that fully declarative rely on the engine to be ready at some point, or to reach the status of the program to be as expected after a certain point. So to do that, you can use, for example, exponential back-off limits. Like, for example, imagine that you want two services to be up and ready, A and B, and these services, A and B, or for example, B depends fully on A. We may think on this like, for example, as an API application and a database. So what a normal run or a billing or pretty naive way of doing this will do is to, okay, I will start both services, and then if the server cannot reach the database, I will restart that server and start it again after a certain amount of time. So then next time it's up, it will reach B without any problem because it was ready, right? This can take longer. If you scale this up to the number of services that we have in Hopsworks, that's why we have 2 hours. When we fully declared the cluster status of Hopsworks using virtual machines, and one tool used before that was called Chef Caramel. On the other hand, if you do this imperatively and you say, okay, first launch A, then launch B, then wait for B to get A to be ready, then you can go really, really fast. But then there is a problem with this paradigm. And the problem is that you really need to write down or to implement the logic, the dependency logic between all the services. And again, then there is a problem with Hopsworks if you consider that we have more than than 10 services and many, many processes in between that needs to wait one for the other. Then how can we decrease this time? So what we did is that we strike a point in the middle by having declarative implementations of the cluster state in the Kubernetes way, using containers, pods, services, stateful sets, etc., and having some sort of imperative way of declaring which service starts before the other, or which service should wait before the other. Why this is important? Let's go to how Kubernetes works at the level of declaring an application. So imagine that you want the application A that uses a container C that run on port P, right? And then internally, this service will depend on service B, which is also launched by container CB on port PB and with many other configurations. What happens is that, as I explained before, if we create both services together, A won't reach B, which means that A will be restarted until a certain amount it will be ready. But the problem with that is that in between, what we have in Kubernetes is we download the image for we download the image C, then the underlying container engine that can be container D, can be even Docker, will spawn this container, this image, right, into a container, and this container will be started at some point, and then we will try to reach B, right? Between this process, all this process can take T0, T1, T2, T3, right? And then when it restarts, because B cannot be reached, it will go again here, right? We want to prevent this loop. This is actually the key behind why a full declarative way of defining the Kubernetes cluster with more than 100 containers running all the time and potentially more created by customers can take up to 2 hours to be ready, right? So what we do is, okay, what if we put something here, like says wait for B, in the most generic way. Notice that this is actually imperative. This is imperative programming, and that's what we have been doing in the Hopsworks definitions, placing generic, let's say, barriers or semaphore in between after the services are up and ready to be connected to a dependent service. With that methodology, we strike 30 minutes deployment of the Hopsworks feature store. Now, we have 2 premises here. We don't want to go fully into the implementing this in imperative way. So what we have been doing with these waits is actually relying on DNS reachability. So when we say wait for B, what we are doing in the end is something like until curl, just to mention some tool, runDB dot namespace dot service dot cluster. Just sleep 1 second. That actually speeds up things, like really speeds up things. And then what happened with more complex logics? So, with more complex logic, we use built-in mechanism of Kubernetes for locking the scheduler, the deployment. For example, we use Kubernetes leases. And in some really weird cases, we rely on the existence of config maps. Right. Yes, so that's how we ensure 30 minutes deployment for Hopsworks. And why this is important. Imagine the previous loop that I saw, the show about the DevOps. That's the first consequence. So we can, 30 minutes against 2 hours. So developers can really do changes, can improve productivity in a daily basis. The other consequence of this is cost reduction, right? So imagine we are implementing this Kubernetes the deployment for Hopsworks, and we want to test this in real life. And by real life, I mean, for example, platforms like our partner OVH. But if you launches the machines and create the cluster and then waste 2 hours for every change, so imagine the cost of one simple cluster in OVH with 30 minutes. This cost is really a trade-off. It made worth we can get a real deployment test with low cost, and we call this the €1 cost. €1 test, and that's another benefit of doing this. But now, how we handle all these mechanisms to work for us without having like 10,000 instructions in the command line to install the cluster, and exactly what I have been doing before starting the drawing. We first create an namespace, and then with the expected kubectl tool, and then so we run 2 commands: kubectl create namespace, and then the other command was Helm install. So the first one, this tool here is the common CLI tool for handling or managing the Kubernetes cluster. And what I'm doing is creating a namespace. A namespace is just a logic separation between services that in the end reach stateful sets or deployments, and these stateful set of deployments are pods, and pods are just a bunch of containers, as we have explained in the beginning. And this logic separation, specifically in this command, what we are doing is creating this space for Hopsworks deployment. And then Helm install, I use something called, I use another term, was Hopsworks release. Then the namespace was previously created. Then I launched this in the root of this migration repository, and then I used some extra tools just for debugging. What I did is, so the first I will start. So this Helm, what is Helm? Well, Helm is a package manager for Kubernetes, and to be honest, it's the package manager for Kubernetes. We put all these services and the orchestration, all these services inside one single monorepo that can be installed with two single command lines. Then, of course, install, which does the work for us, the release name, and this is a logic separation for Helm, because with Helm you can install the same package with different release names. For example, this is actually can be, for example, the book or whatever. Then the namespace in which we want to install, which is Hopsworks, as previously created, and then the repository created. I will show in my computer what this is actually doing and the structure of the folder. But then, luckily for us, we implemented the previous mechanism with barriers and waiting for one service after the other correctly, because actually Helm cannot handle complex dependency or orchestration of the installation of services. Now let's show some code, because drawing is a bit boring. So if you see my screen, this piece of code here, declarative piece of code, actually, it's what I meant. This is the implementation of one of these lock mechanism here. So, as you can see, this uses a container and an image that will be turned in a container. A container is actually an instantiation of an image, right? Then some boring stuff, image with policy, security context, because we care a lot about security in Hopsworks. And then some volume mounts needed for this container to run, and then the command that actually does the magic. As you can see, what we are doing here in concrete is waiting for some specific folders in the HDFS node to be ready. Now, let's see an example of a config map and how we use config maps to ensure that one service cannot run without other service to be ready. And in practice, how this works is that the other service, the dependent service, is the one creating the config map or setting the config map in a way that the other service or the other pod can only be ready after a specific volume mount is ready to be set. And I will use exactly the same code in my screen. And this is, while this is not a config map, it uses the same idea behind. So this container won't spin up without this specific volume to be ready. And as you can see, we implemented a lot of wait for service logs in a way. But again, all of them are as simple and generic as possible to be for developers to be easy to follow and fix and understand. Now let's go back to the very first two command lines I have written. So if you remember, I ran two commands on my terminal. The first one, kubectl create namespace Hopsworks. So this first name here is the serial tool to deal with a Kubernetes cluster in your terminal. And what I'm doing is creating a resource, which is a namespace named Hopsworks. A namespace is just a logical separation for resources in general. And the resources that I mean, in the end, in the very, very top of this abstraction layer, just bunch of containers. And then the second line is Helm install something. So Helm is a package manager for Kubernetes. So you define a bunch of services, pods, containers, all that you need to run in your deployment, and also with a really nice engine template. And this is something that you can actually distribute to everyone in the world, like a simple Helm install Hopsworks. Install, then I did something like Hopsworks release -n, which means in the namespace that we previously created, dot, which means the current folder, it's the definition of the cluster, then --, the book to see what's happening behind. There are several interesting milestones here, right? Here we are installing from a current folder, but what a customer or you will do is just simple helm install Hopsworks, HTTPS, the address of the Hopsworks package directly. You won't need to see what actually we have put it inside this package. But let's go back to my computer and let's see how it's working. And actually, if what I promised, 30 minutes of deployment, it's actually true. Here we go. As you can see in this H column, all deployments or services are green and ready. But is that true? Well, let's see. If we go, for example, Hopworks instance, this is actually one pod running the Hopworks portal. And we just go to this export this port and open it as an HTTPS address. Voila, you have Hopworks in 30 minutes, ready to be tested, ready to be used. With everything, with every service isolated and encapsulated in one single Helm installed command. So the idea here with porting to Kubernetes and especially and concretely to Helm was also to make life easier for our users. So as you can see, we put, like, you can count how many services or deployments we have defined in this folder, as you can see in my screen. But in general, all this complexity is translated to one single command line. Thanks for watching. If you want to try this 30 minutes deployment of Hopworks, please reach out to our website. And if you have questions or any inquiry that we can debate, just please refer to us in our public Slack channel.